Okay. I thought I'd make a quick video to kind of explain the details of why we can say that, at least on the plane and in R3, if we have a closed one form, it's really an exact one form. So there was a homework assignment for which you had to prove this for the plane, the R3, but I'll just work it out for R2 and you can kind of see the details. So what we have, I'm going to say alpha is f x y dx plus g x y dy is closed. So recall that this just means d alpha is 0. And that turns out to be the statement that partial f, partial x, nope. This is what happens when you try to do from memory. So you want to hit it with the y. So fy is partial g partial x. Okay, and there are similar results for if you're working in the three-dimensional case. But we're just in the closed case, and the goal is to prove, prove alpha is d phi for some smooth function phi as a map from R2 to R. Okay, so this is proving that if it's closed, then it's exact in the plane. So it's very important that we're working on the plane and not a punctured plane or anything like that. Okay, so if you want to prove this, at first you can start it out with something like this. We know what the function would have to be by Stokes' theorem, or by the fundamental theorem of calculus. So on one hand, I know that phi would have to take the following form. So in theory, you can say phi at a point x, y is going to be the integral of the one form along any curve gamma, where gamma is a map from 0, 1 to the plane. Gamma of 0 is some initial point, and gamma of 1 is the point in question. So x, y. So this is what it, in theory, has to be just by I guess it's Stokes' theorem, or the fundamental theorem of calculus in one dimension, or in two dimensions, I mean. But you can actually work out what this has to be. So what do I mean by this? Like, let's take our initial point to be the origin, and let's say this is our point x, y. Then I know the function should be the integral of alpha along any path from the origin, for example, to that point. I mean, the reason why there's this choice of base point is kind of in the sense that if you have any two potential functions, phi, they're going to differ by a constant, and that's kind of the idea that's happening. So there's a whole R family of choices. They all differ by adding by a constant. So there's not just one right answer. There's going to be a whole family of correct answers. So I'm going to pick the path gamma to look like the following way. I'm going to first go along y equals 0, and then I'm going to integrate alpha along constant x, and y is ranging up to my y coordinate. So really, if you want to write out what this has to be, if you work out what this gamma has to be, it has two components. If you actually parameterize this, it actually works out that one choice of phi could look like this. The integral of f at t0, and you're integrating from t begins at 0, and you start and you end at x. So that's really this component right here, and we're integrating with respect to t, plus integrating from t equals 0 to y, g 0t dt. That shouldn't be a 0, that should be an x. So really, if you wonder where these things come from, that's actually coming from parametrizing this segment and then parametrizing this segment and adding up the two integrals along those paths, the integrals of alpha along those paths. This is what it has to turn out to be. So I'm skipping that detail, but try to work that out on your own. If you can't see why this really is the integral of alpha along gamma, where gamma is this thing right here. Okay. So to prove that, so if we want to show that the exterior derivative or the differential of phi actually is alpha, which is f dx plus g dy, well, then we have to show that it's enough to show that the partial derivative of phi with respect to x is f, and the partial derivative of phi with respect to y is g. Okay, so let's try to show that. Let's try to show that this thing has those properties. So I'm going to take this to this next page, and we'll take an x derivative, and I'll show that it has to be f itself. Okay. Then you can work out the details for why the partial derivative with y is g. It's a very symmetric argument. So let's do a partial phi partial x. So I'm going to first take an x derivative onto the green piece. So the green piece, well, I'm going to say it's a green thing plus a blue thing. So let's just work on the green thing for a second. And what is the derivative, the partial derivative of that green quantity with respect to x? Well, if you actually work out what the definition of a partial derivative is, you're going to be, it's just going to work out as the following way. This is actually going to be the limit as h goes to 0 of, you're going to take a difference quotient in the x variable. So you'll integrate from 0 to x plus h f of t0 dt, and you'll subtract the same quantity but without the h. So the integral from 0 to x of f of t0 dt. Well, if you actually work out what this is in terms of integrals, this is the limit as h goes to 0 of 1 over h of the integral from from x. You're going to begin it at x, and you're going to integrate to x plus h f of t0 dt. And you're taking, so essentially, this is the average value of f of t0 on the interval x plus h. And as your h gets smaller and smaller and smaller, you can apply a continuity argument to confirm that that thing is actually just equal to f of x0. So the limit is going to be, so this limit is f of x comma 0. That's the green quantity. That's this thing. So that is f of x comma 0. Okay, and if you really wanted, so this step, I don't know if you've done an analysis class, but if you have done analysis and you do know about continuity and you do know about integrals, then you can actually work this out in terms of like a Riemann sum. You can work this out, but I don't know if everybody's taken analysis and really has worked with these limits before, but you are just taking an average value of that function on that interval. So now let's work with the blue quantity. So I'll write it over here. The blue quantity is going to be, well, I'll copy and paste all of this stuff. Copy. Okay, let's take a blue derivative, or sorry, let's take an x derivative of the blue. So let's do this. This is going to be the partial derivative of the following integral. Well, it's a function that depends on x, so we can take a derivative in the x direction. And this is g of xt dt. Okay, so there is a theorem that allows you to do the following. It's called the dominated convergence theorem. And if you've taken an analysis class, then you know about this. If you haven't, then it's okay. Just realize that sometimes the thing I'm about to do isn't always cool. So what I'm going to do is I'm going to flip that partial derivative and that integral. And that works in our case because the function g is very smooth. It's differentiable. It all works nicely. It's C1 at the very least. So we can do this. This is going to be equal to the integral from 0 to y, partial g, partial x, at what point? At xt dt. But this is really where we get to use that closed property. The fact, I'll even show you that closed property said that if I have an x derivative of g, I can replace it with a y derivative for f. So let's come over here and let's replace that. This is the integral from 0 to y of partial f partial y x t dt. And if you can believe it, this is the integral of it's a single integral of a single derivative. So I can actually write this. This is to take us to Calc 1 land, when we talked about the fundamental theorem of calculus, we're doing an integral along d dt of f of x of t dt. And so whenever you have an integral of a derivative, cross cross, you cancel them out, and this gives you f of x comma y minus f of x comma 0. And I'm really getting those numbers. That y comes from up here, and this 0 comes from down here. And so that goes in our blue box. This is f of xt xy minus f of x comma 0. And so we see that, to conclude, this shows that the partial derivative with respect to x does, with this cancellation across cross, really is f of x comma y, which is what we wanted to show. And you can do a similar argument for g if you just work all the things the other way. Okay. And we definitely needed to be able to integrate along every line. So if we had a puncture at a certain point, there would be a problem. If we were working with like a punctured plane, try to see where this argument would fail. That's a good exercise. Okay, I will stop recording now.